In this lecture session, I am going to present the topic on single-phase half-wave control rectifier with R load. Before going into this my lecture session, we should aware of few things. First, what is the difference between uncontrolled rectifier and controlled rectifier? In case of uncontrolled rectifier, we are normally use the particular kind of switch as and good example, that is diode, which starts working 0 to 180 degree. We cannot change the firing angle in between 0 to 180 degree. That is why if diode is actually considered for designing purpose of any kind of rectifier, then the rectifier is uncontrolled rectifier, as the output voltage and current from the rectifier we cannot control or we cannot regulate. Whereas due to application of the control switches like SCR, IGBT, MOSFET, GTO and so on, through which we can design the converter circuit or rectifier circuit. As we know, in case of the discussion of the resistive and capacitive firing circuit, we can change the firing angle alpha over a wide range between 0 to 180 degree. That is why if we can control the firing angle of the each control switch, then the output voltage and current of the rectifier that should be controlled and that should be regulated rather, and that is more viably used for application in industry. And the second thing is, in general, thyristor are turned off as AC supply voltage reverse biases it and provides anode current that fallen to a level below the holding current. The turning off or the commutation of the thyristor by supply voltage itself is called natural or line commutation. So, no need commutation circuit additionally. It is simple and less expensive, and therefore it is widely used in industry where the controlled DC power is required. In the study of rectifier system or any kind of converter system, SCRs and diodes are assumed ideal. Okay, that is 3 points that should be keep it in your mind during operation. Number 1, no voltage drop across them, no reverse current exists under reverse voltage condition, and the holding current is 0. Okay, now we can go through the topic, that is single phase half wave control rectifier with R load. Okay. The schematic circuit diagram of the single phase half wave control rectifier with R load, that is given over here. In this circuit, we are use a AC supply over here, as it is a rectifier operation. That is why we all know that it can convert AC in terms of DC, and that can be happen by using this kind of circuit. So that is why we are using the AC supply over here. A resistive load is considered for resistive load operation, that is R is connected over here, and the load voltage that is defined by VO, and the thyristor is connected over here, that is defined by T, and the voltage across the thyristor, that is VT, and current, that is I0, that is called output current, that can easily flow throughout the circuit, that is defined by I0. And this is the all waveforms we have considered. First, that is Vs or supply voltage, that is Ig, that means the gate current, that is Vo or output voltage, that is IO, output current, and that is Vt, that means that is voltage across the terminal of the switch or SCR. Now, the working principle. Initially, in positive half cycle, due to presence of supply voltage, when the voltage magnitude is increases with a certain amount, and additionally we are giving the gate pulse across the gate, then the switch starts conducting. Once the switch starts conducting, then the current can easily flow to the load, and the load voltage that will be reflected from the supply voltage. And when the switch was not in working state or off state, then the total voltage is appeared across the switch. That has discussed so many times in my previous lecture sessions. So same thing is reflected over here. Suppose we consider this is a supply voltage, as the AC supply is given there, that this is the waveform, and it has the expression that is Vm sin omega t. Suppose we have applied the gate pulse across the gate at an angle that is alpha. So when we have given the gate pulse across gate after alpha, then the switch will be closed. That means then the switch is in on state and it is behaving like a short circuit. That means immediately the supply voltage will be reflected on the load terminal. That is why in case of load voltage C, where the switch, where the alpha point means at which we are giving the gate pulse from alpha to 0, that means the voltage is that should be followed from the input voltage. That means output voltage, the same waveform that should be taken out from, that is input voltage. That is why this is called output voltage waveform. Okay. Now after crossing pi, as the simple manner of the AC signal, that is goes negative. Once it goes negative, as well as no current is existing in the circuit, that is why we can say due to natural commutation, then the thyristor is in off state automatically. So after crossing the pi, the thyristor will be off automatically. That means when the thyristor is off, no voltage is appearing across the load, as the no current is flowing through the circuit. That is why then the total voltage will be appeared across the thyristor. That is why from pi to 2 pi, and when we are giving the next triggering pulse to the next cycle, then the switch will be on. That is why the off state we can consider that is from pi to 2 pi plus alpha. So within this region, no voltage is across the load. That is why the load voltage, that is 0. Then the total voltage is appearing across the terminal, this one. That means then the voltage is, that is what? It should be followed from the supply voltage. That means from pi to, this is the manner of the supply voltage up to 2 pi plus alpha. That is why similarly we should draw the voltage waveform across the switch, that should be from this one to up to the 2 pi plus this one. Means it will be existed in between the space, that is pi to 2 pi plus alpha. Okay. Then we are applying the next triggering pulse to the next cycle, that will be started from after 2 pi, or that is 2 pi plus alpha. Then automatically the switch, then when the switch will be on, then the output voltage that should be reflected on the this one, or input voltage. That means the next cycle will be repeated just in this similar way. That means what we can conclude, that means when the switch is on, then the output voltage that should be reflected from the input voltage, and when the switch is when the switch is open or off, then what happened due to in the case of 0 to pi, and in the case of 2 pi pi to 2 pi plus alpha, then the voltage is appeared across the terminal of the switch. That is why this is the case. So in this way we can explain the output voltage, output current of the single phase half wave control rectifier during the application of the R load. Now we can say from this operation, that is the average value and the RMS value. Okay, because it will give us a pulsating DC like this one, the output voltage. That means as it is a rectifier operation, that means AC that should be converted in terms of the pulsating DC. That is why we are going to calculate the RMS value as well as the average value of the waveform that is appeared across the load, or V0. The average output voltage can be expressed through a simplest way. See, if we consider the average output voltage that is defined by VO average, that should be equal to number of peak by complete cycle integration of confined region voltage expression d omega t or dt. Okay, if here we are considered the output voltage, average output voltage. If we can consider the average output current, the expression will be same. Just we can replace Vt in terms of It. Okay, that is simple means voltage expression or instantaneous current expression that can be replaced by Vm sin omega t. In case of current, that is Im sin omega t. So this is a expression through which we can find out the average value for any kind of wave shape or any kind of output voltage, and after that we can calculate the RMS value, and we know that is root mean square of the average value. So in this way we can calculate the all parameters for this kind of electrical circuit in case of any kind of rectifier circuit. Okay, so we can sure about that the output voltage or average output voltage, that should be number of peaks in any direction. You can consider, normally you can consider for the positive half cycles. Okay, number of peaks in positive side, how many peaks are there, that is number of peaks. And complete cycle means consider the complete cycle, that is maybe 0 to 2 pi and something like that. Integration of confined region, that means that particular peak which is confined to a particular area that is actually defined with the limits. Suppose we consider this is the output voltage waveform, and to get the average output voltage, suppose consider it starts from alpha and it is suppose ended at the point of pi, then we can say it is confined in a particular region, that is alpha to pi, that is called actually confined region. Then we can put the lower limit of the integration, that is alpha, and the upper limit, that should be pi. Okay, something like that. And voltage or current expression, that depends on the parameter which we are going to calculate or find, and that is d omega t or dt. If the axis is defined by omega t, then the expression should be omega t. If the axis is defined by suppose t, then it will be suppose dt. Okay, now we are going to calculate the actual value of the average output voltage and RMS output voltage as well as the currents. So from the waveform, so first go to the waveform. Okay, so in this case it is easily found that the output voltage, this one, that is confined between the region, that is alpha and pi. So whenever we are going to express the expression for average value, then it should be DC, that means average of AC, that will give you DC, that means VDC, that should be equal to 1 by pi. Why? Because in this waveform, number of peaks in a complete cycle means from 0 to 2 pi is a complete cycle. Okay, that is why it is a complete cycle, 0 to 2 pi, and number of peaks in the output voltage, that is 1. So this is a number of peaks, that is 1, because one number of peak is there between 0 to 2 pi. That is why we can express the term, that is number of peaks, that is 1, divided by complete cycle is 2 pi. Okay. Now integration of confined region, where the peaks is confined, see it is confined, that is alpha to pi, that is why the lower limit of the integration, that is replaced by alpha, and that is pi. And this is the voltage, average output voltage, that is why the instantaneous voltage expression that is actually given to the supply, Vm sin omega t d omega t, as it is expressed by the omega t axis, that is why omega t. So after simplification, we can have the result Vm by 2 pi into minus cos omega t, and the upper limit is pi and the lower limit is alpha. By considering these two limits, we can get the result of average output voltage, that is Vm by 2 pi 1 plus cos alpha. Okay. So what will be the result of the average output current? That should be equal to, as we are using the resistive load, that is why average output current, that is IDC, that should be equal to V0 by R. That means V0 means Vm into 1 plus cos alpha. Just we have defined in the previous slide, that is actually Vm by 2 pi 1 plus cos alpha. That is why we can write the expression, that is Vm 1 plus cos alpha divided by 2 pi R. As a resistive load is there, that is why V0 by R, that is why R. So this is the expression for the average output current. Now for RMS value of load voltage. So that is RMS values defined by suppose V RMS, that is roots mean square. Same thing we have done here, that is the value of the instantaneous voltage, and we have taken is the square term, that is Vm square sin square omega t. Okay, same thing, that is number of peaks by complete cycle, that is 1 by 2 pi integration of same thing, that is alpha to pi. So this is the actually the expression for the particular peak, that is 1 by 2 pi integration of alpha to pi Vm square sin square omega t d omega t and under root, as we are going to find out the RMS value. So after simplification, we will have that is Vm square by 2 pi integration of alpha to pi sin square omega t d omega t. Then we can modify the expression Vm by 2 pi into 1 by 2 integration of alpha to pi, that is alpha to pi, that is alpha to pi 2 sin square omega t d omega t under root. That means we can say Vm square by 4 pi integration of alpha to pi 1 minus cos 2 omega t. As we know, 1 minus cos 2 omega t equal to 2 sin square omega t. Okay, just we have changed this the formula. That means d omega t this one. So further we can express the expression that is Vm by 2 root pi, that is means the integration part of 1 or constant, that is omega t. Okay, and it is cos 2 omega t, that means 1 by 2 sin 2 omega t. And considering this upper limit and lower limit of the expression, we can say that is Vm by 2 root pi under bracket pi minus alpha plus 1 by 2 sin 2 alpha under root. So this is the final expression for the RMS value of load voltage. Now, in case of the RMS value of the load current, that is again we can say that is V RMS by R, right? So I RMS equal to V RMS by R, that is equal to Vm by 2 pi R, and the remaining parts are same, that is pi minus alpha plus 1 by 2 sin 2 alpha under root. Now we can calculate the power. So the power delivered to the resistance from the supply, that can be replaced by PAC. Okay, because the power is delivering from the supply, as we are using the AC supply, that is why we can write the term that is PAC, P for power and AC, as we are using the AC supply, that is PAC, that equal to VRMS into IRMS. So already we have explained the part that is VRMS and IRMS. Just we have put it the value, that is Vm by 2 root 2 under root pi, that is pi minus alpha plus 1 by 2 sin 2 alpha, and this part is IRMS part, that is this one is IRMS, that means Vm by 2 pi R under bracket means pi minus alpha plus 1 by 2 sin alpha under root. So after calculating this expression, we can have the value that is Vm square by 4 pi R pi minus alpha plus 1 by 2 sin 2 alpha. So PDC, that is equal to VDC into IDC. Just we can calculate this expression just like a PAC, that is we can multiply the both term, that is VDC, that is this one, and IDC this one. VDC means Vm by 2 pi 1 plus cos alpha into Vm by 2 pi R 1 plus cos alpha. After multiplication these two terms, VDC and IDC, we can get the actual output average power or PDC, that is defined by Vm square by 4 pi square R into 1 plus cos alpha whole square. So this is all about for the half wave rectifier during our load operation. So thank you.